Hi, welcome to the EEVblog, an electronics engineering video blog of interest to anyone involved in electronics design. I'm your host, Dave Jones.
Hi, it's lithium-ion battery tutorial time. Why? Because these lithium-ion battery cells that you can get these days from hobby suppliers, professional suppliers, whatever, are great for designing into your next product or gadget that you want to build. Now, when you build a gadget, you want to build in some rechargeable batteries, you have a couple of choices. One is your traditional nickel metal hydride rechargeable AA, AAA, whatever, batteries, right? Well, they're a bit of a pain in the butt. They're old hat chemistry, they're a low terminal voltage, so you've got to often wire a lot of them in series to get the voltage you want, and they're just, big pain in the butt, not available in really nice tiny shapes and sizes like these lithium-ion cells. Here's a 230 milliamp hour cell. Here's a 50 milliamp hour cell. You can get these from companies like powerstream.com and many other places, hobbyist outlets for remote control stuff all over the place. And as it turns out, they're cheap, readily available, and really easy to use in terms of charging circuitry and stuff like that. So we'll go into it. And you've seen your standard Nokia 3.6 volt nominal battery, or actually this isn't quite a battery pack, it's actually a single lithium ion cell, because a battery pack is multiple cells like these in series, and you can get those and they charge exactly the same way. But we're going to stick to the individual lithium ion / lithium polymer. There's no real difference between lithium ion and lithium polymer. Don't fall for it. It's a bit of a marketing gimmick. Okay, so we're going to take a look at these, how you can charge them, how you can build them into your next product. Let's go. And the great thing about these cells, as I said, is their size and shape. Take a look at these. They're only a couple of millimeters thick, and they come in various sizes. You can actually get them under a millimeter thick. They're actually flexible. They're absolutely amazing. So if you're designing something really weird and unusual, say I'm designing my new calculator watch or something like that, right, I would use one of these because they come in a whole variety, hundreds of different shapes and sizes. You just pick one that's optimized for your particular purpose. Fantastic. Now let's take a look at the standard characteristic discharge curve of a typical lithium-ion / lithium polymer. As I said, no difference whatsoever. Don't let anyone fool you otherwise. Okay, lithium-ion cell. That's just one cell. Remember, not a battery pack. A battery pack will have 2 or more cells in series, but we're only going to consider the one cell. Now, you'll notice this curve if you've seen some of my other tutorials on the AA nickel metal standard nickel metal hydride batteries, alkaline batteries. They all have a very similar characteristic curve like this. They all start off at a particular voltage. Sometimes they drop a bit quickly, and then they have sort of a flat, slopey kind of bit, and then they drop off fairly abruptly at the end. And lithium-ion, lithium polymer batteries are no different at all. Now, there are actually 2 different types. Don't confuse these with lithium ion and lithium polymer, because they're the same thing. In fact, they're the new type of anode material. I won't go into the construction of batteries. You can look those up yourself. But the anode in there can use 2 different types of materials in lithium ion batteries. The first one they ever used, and is the traditional type, older type, uses a coke material, not to be confused with the trademark Coke or the other type of Coke. This actually comes from coal. It's actually derived from that. Or the new modern ones. In fact, the vast majority of lithium-ion batteries you can buy and lithium polymer batteries will have a graphite anode. Now, the advantage of the graphite anode one, as you can see, it starts off and maintains a higher voltage for a longer amount of time, and this is flatter. The curve here is flatter than the Coke anode one, and it drops off much later in voltage as well. So the advantage of that is that you can power your 3.3 volt circuit, a modern circuit, microcontroller, whatever, at 3.3 volts directly from the battery using the low dropout voltage regulator. Because if your circuit is 3.3 volts, there it is, okay? But you might use a linear low dropout voltage regulator, might have a dropout voltage of 0.1 volts or even 0.2 volts. Even at 3.5 volts dropout voltage, you're using most of the capacity of that battery. It's fantastic. Now, the difference between a graphite one is typically determined to be dead at around about 3 volt level or something like that, and a coke anode, the older type batteries, are typically taken to be dead around 2.5 volts, 2.6, 2.7, something like that. Even some of the graphite anode ones are determined to be dead at 2.7. Now, these curves will vary by manufacturer, they'll vary by battery type, slightly different process variations in the manufacture of the battery, all sorts of stuff. But these curves are going to be very similar, and they're handy because you can power your 3.3 volt circuits directly from one of these little lithium-ion cells. Fantastic. Just something quick, I forgot to add that the x-axis here is actually time or capacity, like from 0 to 100% the capacity of your battery, or C as it's called, or it could be 0 to 1 hour or 0 to 10 hours in terms of time. Makes no difference, but that is the standard characteristic curve of a battery, the voltage of the cell versus time or capacity. So, how do you charge one of these lithium-ion cells? I'm glad you asked. It's pretty darn easy, regardless of how complicated all this stuff here looks. It turns out to be pretty simple, so stick with me. Now, when you charge the traditional nickel metal hydride batteries and stuff like that, they're a bit of a pain because they're an exothermic thing, so a lithium ion as well, but really to charge them properly you should sense the temperature of them as well to determine, as well as the voltage on them, to determine when to stop charging or when they're full. Now, with lithium ions, you're supposed to do the same thing, but these small capacity ones, if you charge them at a low enough current, you don't have to worry about sensing the temperature of them to determine when when you've finished charging these things and it's full. Really, a lot of the charger chips on the market, which we'll go into, they do have built-in temperature interfaces for temperature sensors which sense the cell, but really that's just not to detect that the cell is finished charging, just to really actually protect it from gross overloads and things like that. If it shorts out, something goes horribly wrong, something like that. So to charge them is really easy. Any lithium ion or lithium polymer cell, they charge exactly the same way. As we said, there's only two differences. One is, well, the only difference is the charge voltage, which we'll have a look at here, 4.1 volts or 4.2. That value is very critical. It's got to be within like 1% or something like that. So that's why you'll find that most, all lithium-ion charger cells on the market will be 4.1 or 4.2 is the most common by far, volts plus minus at least 1%. Some are capable of going down to 0.3 or 0.4% accuracy. And I won't go into it, but you can look up the research yourself. Lithium-ion batteries, their shelf life and their number of recharges is pretty much directly, or the biggest factor, directly proportional pretty much to what maximum voltage you actually charge them at and the charge rate as well. But that voltage, critical, okay? You've got to get it right, but the chips handle it for you, so don't worry about it. Just giving you some background info. Now, to charge a lithium-ion battery uses what's called a constant current and constant voltage process, or CCCV process. Constant current, constant voltage. It's a two-step process. I've got 3 steps here, but the first step is actually optional. So we're only going to deal with step number 1 and step number 2. And it's really quite easy, and the chip does handle it all for you, but I'm just explaining how it works if, well, you really should know, because it's interesting for starters. Okay, now, the y-axis here, we've got volts in green. Okay, so the green curve here is the battery voltage, the terminal voltage of the battery during the charging process. This is time on the x-axis, And the blue curve here is the battery current, or the cell current. Now, the current, this is important. If this little thing here is a 50 milliamp hour battery, which is what it is, okay, then that is called 1C, or 1, that's the charge rate. It's just called C, or 1C, okay? Now, lithium-ion batteries, make sure you always check the data sheet for your cell, but most of them will be charged around typically 0.5 C. So if this is 50 milliamp hours, or 50 milliamp hour battery capacity, or 1C, we'll charge it at half that rate, or 25 milliamps. So this blue curve, which is the battery current, 100% actually means 25 milliamps, or half C. Some of them can be charged at 1C if you want to charge them faster. Some, maybe you can even charge them faster than that, but we're not going to go into it. A typical thing for one of these low capacity lithium ion cells, half C. So that 100% means, in this case, 25 milliamps, from 0 to 25 milliamps, and voltage, the green curve, from 0, in this case, 4.2 volts. Now, it starts off at, ignore this one called pre-process, okay, we'll go into that later, but it starts off with a constant current process. As you can see, the charger just goes from, 0, right? It goes from 0 to 100% charging capacity, or half C, 25 milliamps. So it sits there for, I don't know, it might sit there for an hour, whatever, okay, it depends on the capacity of your battery. And during that time, it's pushing a constant current into the battery. It's a constant current process. And as that happens, the cell voltage, assuming the cell's already dead, okay, at 2.8 volts there, let's say the battery is 2.8 volts when you start charging, it'll slowly rise like that, fairly sort of linear, and then it starts to taper off like that until it eventually gets to 4.2 volts, which is the upper threshold, or the float charge voltage threshold. And it goes by many different names in the data sheets and stuff like that, but that's the float charge voltage. And once it hits that point, that very critical voltage point, got to be within like 1% or better, then it changes modes from constant current charging into constant voltage charging, where all it does is now, instead of pushing a constant current into the battery, it maintains that it goes constant voltage 4.2, just like a voltage regulator. In fact, it works exactly like a linear regulator, as we'll check out down here, and it keeps it at that 4.2 volt level. But what happens to the current, I hear you ask? Well, it actually starts to drop and taper off, and it takes quite some time until it gets down to a threshold level down here, which is actually set by a percentage of your charge current. So if charge current's 100%, this is why I called it 100%, because this is what they call it in the data sheets when you look at it. The value that it stops charging at is deemed to be full, okay? So this value down here, your battery is full, it's fully charged, Bob's your uncle, okay, is typically taken at 10% of the full current. So if this was 25 milliamps, constant current charging level, once the current level got down to 2.5 milliamps for this particular little tiny cell here, then bang, it stops charging, and that's it. Fully charged battery. Whew, piece of cake. Now, that two-step process is what's required to really utilize the full capacity and the full life of your battery. But some cheap chargers and very fast chargers, quote marks, will actually just totally skip this constant voltage process and just do constant current and then stop when it gets to 4.2 volts. And it's still going to have, say, 80 or maybe even 90% of the battery's full capacity if you just do this mode. So this mode here may take an extra hour or something, and you may only get an extra 10 or 20% out of it. So you've really got to weigh up, the pros and cons of actually doing that. But all good battery charger, lithium-ion battery charger chips will be a two-step process, and they'll only stop when they've finished this constant voltage charge process. Now, what's this first stage here, I hear you ask? Well, it's called the pre-charge stage, and this is used, some lithium-ion battery charger ICs have this mode, some don't, but your good ones will. This mode will only be used if the battery voltage, when you first turn on that chip and it measures the battery voltage, if it's less than the pre-charge voltage threshold, goes under different names depending on the manufacturer and the data sheet, but typically around, say, 2.8 volts, that battery is deemed to be really dead, fully dead. It needs rejuvenating, okay? So it needs to be fixed. If you get a really completely dead cell that's only got 1 volt on it, or half a volt, or no volts on it, okay, you've really left your product on, it had no low voltage cutout, the cell, it's completely killed the cell, you can rejuvenate it, but you can't just jump straight into 100% current, because you'll further damage the cell, you'll ruin it. So what they do is they have a pre-charge process where it only charges it at typically 20% of the full capacity. Now that value varies, as does this full charge value. These can vary. Some chips even allow you to adjust this and this as well as the charge current, and they're your really flexible chips. But typically, if you plug your charger chip on and it measures that the voltage is less than 2.8, it will only apply 20% of the current until such time as it reaches 2.8, and then it'll go into the next constant current process. So what's this circuit down here? Well, this is very simplistically what's inside a lithium-ion charger battery chip. They can be incredibly simple, so simple that they can only have 3 terminals on them, really. If they have a fixed, there's an input terminal where you plug your charging voltage in, there's an output terminal which goes to your battery, and there's a ground if it's got its own built-in voltage reference and it's a fixed charge current. Some chips might charge at, say, 0.5 amp or 100 milliamps or something like that, fixed. You can't change it, and it all handles it internally. A slightly more advanced charger chip might have an extra pin which allows you to typically set the charge current with a single resistor, because that will actually be a percentage. We'll go into it anyway. It allows you to set the charge current with that value resistor. There's a little formula in there, varies by the manufacturer and the type of chip, but it allows you to calculate, okay, I've got my little 50 milliamp hour battery, I want to charge that at half C to be on the safe side, 25 milliamps. I would plug 25 milliamps into the formula in the data sheet, and that would give us a resistor value that allows this chip to charge constant current here of 25 milliamps. And to do that, most chips, the fully integrated ones, will have a built-in current shunt sense resistor there with a little amplifier, with a little differential amplifier there as well, and a series pass transistor or a series pass MOSFET in there, driven by an op-amp. And you've seen these type of circuit configurations before. Now, this pass transistor can, depending on, there's a lot of control circuitry in here and voltage references and stuff like that that go between the different modes, but you don't have to worry about that. When you've got a pass transistor like this, you can make it operate in constant current mode like this by determining the voltage drop across that shunt sense resistor there. You can keep it at a fixed current, and then when it switches into another mode, it can work as a linear voltage regulator. And that's why these are typically, lithium-ion charger ICs are typically a linear type, because they drive the pass transistor with a DC voltage. It's a linear thing. Some will actually drive this with a pulse width modulator, okay? And there you switch mode types, but you can look at the data sheets to see the differences between those. But most of the simple ones, and there's nothing wrong with them, most of them will be of the linear type. The switch mode ones are more advanced if you want to get greater efficiency based on various input voltages and stuff like that. Anyway, these automatically charge the battery using this 3 or 2-step charging process, instantly determine the current flowing through the cell, and they determine the voltage on the cell. They've got built-in voltage references, and they do everything for you. And you can just hang your circuitry via a low dropout voltage regulator, as we mentioned before. If you're powering a 3.3 volt circuit, no problems at all, hang it straight off. But always remember, when you're charging, that your circuit will also take a certain amount of current as well. So you have to take that into account when you calculate this value up here. So if our circuit was taking an extra 25 milliamps, then our cell at half C25, we'd need to set this value to 50 milliamps to cater for the current down into the cell and also to power the circuit under test. And the good thing about most of these lithium-ion charger chips is that you can leave them permanently connected to the cell like this, and when they're finished charging, they will actually stop. They won't draw any current back out of the cell like that, and they'll actually have diodes built across the built into the pass transistor here to actually stop if you physically remove or short out your charger input. It won't drain the battery back out of it. And you can get specs for the current that leaks back out of the battery. It's usually quite small, in the order of microamps or sub microamps or something like that. So you can really leave these things just permanently hooked on to your circuit under test. It's fantastic. So if you've got if you've got a product that, say, goes into sleep mode all the time, it's got no on-off switch, it just wakes up, then you can just leave all this permanently attached and you've got no power switch whatsoever. Brilliant. Okay, let's take a quick look at some lithium-ion batteries that you can get on the market. I'm using powerstream.com, which is a provider of a whole bunch of battery cells, some of the largest selection on the market. So let's go into batteries and packs down here and check out some of these. Now, there's some primary lithium batteries, but look at these babies. Ultra-thin, rechargeable lithium polymer / lithium-ion batteries. 500 microns, from 0.5 millimeters to 1 millimeter thick, and you can bend them. If you've got a product which needs to be flexible, like you can't just put a square battery into it, like if you've got something that's mounted on your wrist, you want to wrap the whole battery around your wrist, no problems whatsoever. Awesome. But let's go into, say, the standard lithium polymer cells here, and let's take a look at the whole range of them. They're all nominally, don't worry about the nominal voltage, that's just the average voltage. They're all actually I believe they're all the standard 4.2 volt variety, but you'd have to read the data sheet for that. But you can get them in capacities as low as 8 to 12 milliamp hours, really tiny stuff. But let me tell you, it is very, very difficult actually to find a lithium-ion battery charger chip that actually handles battery capacities that small. So just be wary of that. It can actually be difficult because most lithium-ion battery charger ICs are actually optimized for, half an amp or 2 amps or something like that. And then it's a bit of a trade-off between the circuitry inside is designed for those for current and voltage current accuracy at those sort of currents. Yet if you try and charge them at very low currents, like if this is a 12 milliamp hour nominal cell, you would have to charge that at half C or 6 milliamps, then the current accuracy of those battery charger chips is going to be very difficult to get at 6 milliamp hours. And I've tried to find some, and trust me, they can be quite difficult. So just be wary of that if you do go that low, if you're designing ultra tiny products. But check out the size of these. Dimensions: 3 by 9 millimeters, 2 by 4, and 18 by 5.2. And there's countless different sizes and thicknesses and capacities and things like that. And here's the data sheet for that particular battery we just chose. It was one completely at random, and there it is. The charging voltage is 4.2, so it is a graphite type anode, plus minus 0.03 volts. That is quite tight indeed. That's why you have to have a very accurate dedicated lithium-ion charging IC that has that sort of accuracy. And then, as you can see, it actually recommends a 0.5 C, constant charge rate for a standard charge. If you do want to do a fast charge, it can do it at 1C. And then the cutoff, you remember that actual percentage value we were talking about? There it is, 0.01C. All right, let's do a quick search here using DigiKey for a suitable battery charger IC. For that example battery we were using before, the little 50 milliamp hour capacity battery, and I'm going to charge that at 0.5C or 25 milliamps. So let's type battery charger into DigiKey search here and see what we get. If we scroll down here, we've got battery management ICs, 2,529 of them. And as you can see, here's the parametric table. There's a different battery chemistry. Now, unfortunately, DigiKey don't let you select the charge voltage because it doesn't really know, even if you go drill deeper into the specific lithium-ion batteries here, which we can actually do, but it still doesn't know the difference between those, so it won't give you an extra charging voltage. It's got supply voltage here, but it'd be nice if you could actually choose 4.1 or 4.2 volts, but it doesn't do that. But I know most are going to be 4.2 anyway. So let's choose a manufacturer which we like here. Now, it hasn't popped up with, strangely, it hasn't popped up with Microchip. Microchip's actually the one I wanted. That's a bit of a fail there. Maybe there's an extra, there we go. I didn't actually choose, it must be in those categories there because they're multi-chemistry devices. Just be careful of that. You can actually miss quite a few manufacturers if you don't select the correct actual battery chemistry here. But we can just ignore that. We can just reset that and say, I want Microchip parts because I know Microchip parts are in stock. I like them. They're cheap. They're small. They work. So I'm going to try those, and as you can see, most of them are lithium-ion based ones, but let's go for the in-stock parts, shall we? And let's have a look. We've got 80 items. Well, let's just view those. I'm happy with that. And what's first cab off the rank here, we could actually search by price if we were price sensitive or something like that, but the MCP 73 812, MCP 73831, you can actually get those for 42 cents each for 3,000 or 68 cents for one off. So they're very cheap. They're in a 5-pin SO SOT23 package, and that's incredibly small, simple obviously, and there's 21,000 in stock. I'm happy with that. I'm actually going to check out the MCP 73831. Let's take a look at the data sheet. They call it a miniature single cell, fully integrated lithium-ion, lithium polymer charge management controller. Fantastic. It's a linear one. It says it's an integrated, it's a linear type device. It's got an integrated pass transistor, it's got integrated current sets, and it's got reverse discharge protection, which we also mentioned, which is great. So when you disconnect the input, it doesn't drain your battery on you. It's got high accuracy, pretty good, better than the standard 1%. It's got plus minus 0.75% there, which is really nice. I like that. You can get it in 4 different options for different chemistry batteries, but we want the 4.2 volt device. Just make sure that you order the right one. Some of them aren't pin selectable. In fact, most of them won't be. They'll be a fixed voltage. So just make sure you do get the 4.2 volt or whichever voltage for your particular cell, which you'll get on the data sheet. Now, programmable current range. Now, here's where I mentioned before, not all of them will go down to a low current for very low capacity batteries, but this one says it'll handle from 15 milliamps up to 500 milliamps. Great, we need 25. It'll be within the ballpark on the graph, as we'll see later. Fantastic, it'll still maintain its current accuracy down to 15 milliamps. It's got selectable preconditioning, that pre-charge, that actual rejuvenation charge, 10, 20, 40, or you can actually disable that if you don't want it at all. And it's got selectable end of charge control too. But because, as we'll see down here, there are hardly any pins on it at all, I think those options will actually be a factory option and not a pin settable
option. So just be careful of that. Larger pin count devices are more flexible. They will have they will often have these settings on a separate pin with a separate program resistor. You just choose the right value of resistor and you can set your end charge control to anything you like. But I don't think this device will have that. Anyway, it's got thermal regulation. It automatically powers down. It's nice. It's in a you can get it in a tiny 2mm by 3mm DFM or an easier to use 5-pin SOT23. Fantastic. I like it. And this is the typical application. This is how simple it is here. Your voltage input from your charger, decoupling cap, your output voltage, you've got to have a decoupling cap on there, otherwise it can oscillate, just like any linear or low dropout voltage regulator can. Same thing here, the internal charging circuitry is the same, similar circuitry to what's used, and it will be an unstable loop unless you add the output, the recommended value of output capacitance. So just make sure you do that, and it's got ground pin and a programming pin, which allows you to set the programming current, and it's got a stat output which can drive an LED to presumably tell you that it's finished charging. And here's the internal circuitry for it. It's not much at all, but as you can see, your input pin here, your battery output pin here, here's your pass transistor with the internal blocking diode, so it stops discharging from the battery. There's another smaller pass transistor there, reference voltage generator, a whole bunch of comparators for your different modes, your preconditioning mode, your termination mode, your end of charge, and all that sort of stuff. And and there's your stat output pin that's only available on the 73831. The 73832 presumably doesn't have that pin. If you don't want it, you can probably save half a cent there or something like that. And as you can see, there's not really much in them at all. Voltage, a couple of constant current generators and things like that. But they're pretty simplistic devices because they don't really have to do much at all, apart from transition from a constant current mode into a constant voltage mode. And to do that doesn't require much circuitry at all. Its supply voltage range from 3.75 to 6 volts. Brilliant, not a problem. Let's look through some of the other stats here. As you can see, the regulated output voltage, 4.2 volts. There's the different part numbers that you can buy with the different charging float voltages. Make sure you get the right one. Don't want to goof that up at all, otherwise you'll be in big trouble and you'll damage your cell. And there's the current regulation. It looks like it's got plus minus 10% current regulation there, which isn't too bad. The precondition current is set to 10%. Now, the program resistor, 2K to 10K, I don't know what's going on there. The precondition current, this seems weird. They've got the same condition over here, yet different values. I think that's a datasheet mistake. Anyway, not sure what's going on there. Aha, here it is. I've scrolled down to the product identification system right at the end of the datasheet, and this clears up the confusion we saw before with the pre and post current termination ratios that were, it said, were programmable. Well, they're programmable as factory options. So up here you've got the part number. You've got to order exactly the right option. The options are AC, AD, AT, DC, and they give you various options for the pre and post charge termination and other things. So you've got to make sure that you order exactly the right part. Otherwise, you could easily end up with being actually delivered or ordering the wrong part, and that could slip into your product, and you can wonder why your battery charge performance isn't as good as your prototype and your testing showed, because you might have the wrong part. Something to be wary of. The precondition voltage on this is quite high. It's 66.5%. That's much higher than the 20% I said before, but many chips use different, lots of different value default ratios for that sort of thing. Now, the charge termination ratio by default is 5%. And the charge termination, once it reaches 5%, as we saw on that curve, it will actually turn off and you finish charging. Pass transistor on resistance. There's the battery discharge leakage, okay? So when it's finished charging, it will only take 0.15 microamps, and under the various conditions, So it doesn't take much current at all. Once the charge is complete and it's still got the input voltage on there, it takes up to 5.5 or maybe even as much as minus 15 microamps from your battery. So just take that into account. This isn't the lowest power device I've seen in terms of off-state leakage current. And if we look at some of the characteristic curves here, these are very interesting. Now this is an important one here. This is the charge current on the y-axis in milliamps versus the programming resistor. And as you can see, they give a range in the data sheet above for 2 to 67K or something like that. But as you can see, it is not a linear type thing. So you can't just arbitrarily put in like a 100K resistor or a 1 meg resistor and get really low charge values, because then the current accuracy is going to be all over the place and it's not characterized on this curve. So really it looks like that value there, if you extrapolate across there, it goes down. Well, it tells you above that it was 15 milliamps, and that's sure enough on the graph it looks like about 15 milliamps. That's really something to consider when you're choosing these chips for low value, low capacity, ultra low capacity batteries. And last of all, I'm just going to take a quick look at a more flexible charging IC, the ST Micro L6924D. You'll find that it's got, it says it's got programmable pre-charge current, programmable end of charge current, programmable pre-charge voltage threshold, and it's got a programmable charge timer as well, which will be a backup device just in case the voltage cutout doesn't work. It'll have a fixed time and then cut off just as a secondary safety feature. And it's also got an NTC or PTC thermistor temperature interface, which will limit the charge current if the temperature of the battery goes up past a certain setting. Now let's take a look at the you can see here that it's got different resistors on here to charge to change those various aspects of the charging cycle, the pre and the post charge current. Now if we go down here and take a look at the internal block diagram, it's got there's the pass transistor as well. There's V in here, V out on the right here, which goes to the battery. It's got current detection, fault detection logic. There's the diode that actually blocks it as well. It's got a gas gauge function as well, and this is what a lot of devices will have if they actually use the if they use the resistor to set the charge current. It actually drives a current through that resistor which is proportional to your charge current. So you can hook that up to an ADC on your microcontroller and you can actually log how much current is going into your battery during charging. It's quite nice. So that's just a more flexible IC that just allows you to do a fair few more things than the microchip one we saw before. So if you really have to get a really precise value of charge and capacity and long life in a professionally designed product, you would use a more advanced IC like this, and you would go through all the various aspects and you would design it properly so that your built-in battery would have the longest life possible. And if we take a look at the final application demo circuit down here, as you can see, it's just got programmable, these resistors here program all the various aspects of the charging cycles. So there you go, that's a more advanced one. There's simple ones available, some real dumbass 3-terminal ones, take your pick. But lithium-ion battery charging is pretty simple with these dedicated ICs. So next time you're designing a product and you want to build in a recharging solution, use lithium-ion. The cells are incredibly versatile in shape and size, low cost, the chips are dirt cheap, readily available, easy to use. Go for it. Hope you enjoyed it. See ya.